Yeah, we're going to get started now as people are still drifting in. Yeah, I'm one of the session chairs along with Joel Jensen from Anglo. And I just want to make a very brief introduction, and I want to start now so we don't waste the speaker's time. Yeah, this session is in-mine and camp scale exploration. I asked John McGaughy what that meant, and he said basically very data-rich environments. So of course, one of the themes of this conference is data integration, and these, the in-mine and near-mine, which is brownfields, are very fertile fields for data integration and the very rapidly developing field of data analytics. So we thought that was a pretty good thing to focus on for this. And also, the near-mine and the brownfields area has been one of the most productive areas for exploration. So we're very pleased to have four great speakers today. We've got a couple people who are going to be talking about big data analytics, machine learning, big data, whatever you want to call it. And in my opinion, this is maybe the fastest developing thing and maybe the newest thing we're looking at. It didn't really exist 10 years ago. And I think 10 years from now, it's going to be a pretty big part of our work. So it's worth keeping an eye on. And we have a couple of the top experts in the field today. The other thing that's happened in the last 10 years, and I think maybe one of the biggest changes in any of the methods we're working with, is in natural field EM, and Joel's going to be talking about that. And it's evolved very rapidly from kind of maybe a bit of a fringe tool a few years ago to a mine finder and mineral system identifier. Now, and I think particularly with the use of 3D and airborne natural field methods, it's a very powerful tool. So I won't take up any more time, and I'll turn it over to Guy after I read his bio.
Alejandro? Check. How are you? Yeah.
Guy obtained his PhD. Oh. Hello? Okay, I'm on. Yeah, Guy obtained his PhD from the University of Manitoba. His thesis focused on belt-scale geochemistry of mafic, ultramafic rocks and related sulfide mineralization. He began his career as an exploration geologist with Xstrata Nickel in the Raglan Nickel Belt. He completed a wide range of projects internationally while working with SGS, including resource estimation, economic evaluation, geometallurgical studies, and audits of resources and reserves. In particular, he led the team which won the Integra Gold Rush Challenge in 2016, and he was recently named Distinguished Lecturer by the CIM for his work on metallurgical sample selection and fatal flaws in resource estimation.
Thanks, Alan. I'd like to start by thanking first Alan for inviting me to give this talk, as well as the organizers for the conference. My previous explorer, SGS, and my current explorer, my employer is Cisco Gold Royalties. So today I want to talk about particularly the use of machine learning and how we can use that to leverage our data and make discoveries. So the question is, should we transfer our data to Johnny Geologist or Debbie data scientists and ask them to discover the next deposit? The quick answer is buyer beware. A lot of the tools are very easy to use and very dangerous to if they're applied without enough caution and robust models. And my goal is to scare everybody here a little bit and make sure that we have in place enough processes to ensure that the results of these data analytics gives us something robust and something that's actually going to add value to our projects. Cisco Gold Royalties is basically a royalties company. We invest in mining companies. In exchange, we get future consideration. So the reason why Alan invited me is I was part of a group that participated in the Integra Gold Rush Challenge. So it was basically a competition where this junior mining company released all of their data and then challenged the world to give them the best possible exploration program. The first prize was $500,000, so there was a lot of excitement, a lot of participants. These are my two co-workers that we were the principal people worked on this project, and we put together a fairly compelling product which combined weight of evidence, machine learning, virtual reality, and at the end really using some logical steps to really come out with the best targets and best suited for this client in particular. At this very moment, this is the PDAC in 2016, so I'm on stage there presenting, and at that very moment, I'm not a machine learning expert. I had asked my colleague, Doug, to use whatever methods he could find to really leverage the data and use something a little bit out of the box. But by the time that we had won the competition, I had to become an expert very, very quickly. So that gives you an idea of how low the bar is to become an expert in data analytics at this point. A year later, I've educated myself. We developed some things with SGS to different machine learning techniques and also the workflow to really come out with the best possible solution. What's the goal of all of this? You've probably seen this graph a couple times. So this is Shadi's compilation of the discoveries over time, and the red line represents the expenditures. So now, in the past 10 years, we're a lot less efficient at discoveries. So what are the tools that we can add to really optimize future discoveries? And I think machine learning, we're going to see more and more of that, and it's probably going to be a small part of the future discoveries if we're going to see any uptick in the efficiencies. So when I talk about big data, I mean, people in this room here, I think, are already know what's out there. There's been tons of great talks and great new technologies out there that are going to add value. I think one of the trends that we're going to see in the future is a lot more higher number of qualitative type data, so the handheld XRF or handheld XRD, hyperspectral, and then we take that data and we sort of use them as proxies for recovery or vectoring towards ore deposits. And hopefully we'll continue to steal from our friends in the oil and gas industry who tend to be a couple steps ahead of us in terms of the application of technology for discoveries. So one of the great examples of the application of machine learning is in the field of autonomous driving. So in 2005, the US Army was losing having a lot of casualties in Afghanistan due to roadside bombs. So they put out a challenge to say, well, how can we increase our safety factor? And they said, well, let's have the trucks drive themselves and we have fewer people in the field. So they put out this challenge and about 15 teams participated. In the first year, you had all these different types of vehicles with cameras and LiDAR on the vehicles. Most of them did not leave the arena. They saw their shadow and freaked out and stopped. A few got out of the arena, turned a few corners and saw a cactus and freaked out and stopped. 1 year later, almost half the teams completed the course, so several dozens of kilometers, including Stanford, who took the first prize, and they were driving at an average of 50 kilometers per hour. So if we could advance our technology as quickly as they did with autonomous driving, that would be amazingly incredible. I don't think that we're going to do that. So what happened between those 2 years? The sensor technology didn't change that much, so the data that was taken in wasn't that much different. The algorithms that were used probably advanced a little bit, but the main difference was they had enough data to teach the algorithms to recognize the difference between a shadow, a cactus, or a cow crossing the road. And today, before the end of the year, Elon Musk has predicted that they'll have a car drive from Los Angeles to New York without anybody touching the steering wheel. So this is going to happen. It's coming soon, and it just gives us an idea of how we're going to be, where we're going to move in the future. And specifically for mining, I think this is going to have a huge implication for mining costs and how we're going to develop mines in the future. 5 years ago even, if you wanted to apply machine learning techniques, you had to be a coder. You had to know how to make code in Python, and you had to have a really strong background in software design. Today, actually, anybody in this room can go on the internet, go on this website provided by Microsoft, figure out which are the best techniques given the problem you're trying to solve, upload your data to the cloud, click a few boxes, play around with the parameters, and it'll spit out a beautiful result. It even gives you QA/QC, which gives you very good confidence that you're doing things correctly. And at the end of the day, then you're off to the races. So for me, it's a little bit too easy, because the real difficult part of this process is feeding the machine learning algorithm real, robust data and interpreting and cutting out things that are going to cause spurious results. So what are some of the problems we have with the data we're going to feed these machine learning algorithms? First of all, a lot of the data is very clustered. The very best data we can have is drilling, that's the truth. And along that drill hole, we can send a bunch of geophysical tools down the hole. We can do hyperspectral logging, assay, all the geochem we want to do. But that data is very clustered around things we already know. We want to discover new deposits, so how do we extrapolate that data? That's one of the big challenges. Another is machine learning algorithms tend to like having equal examples of positive and negative examples. So if you want to train a machine learning algorithm to recognize a dog, then you have to feed it, a million pictures of dog faces and a million pictures of cat faces. And typically we don't have enough of either one of those. Typically we have too much waste examples. Another problem is we will teach the machine learning algorithm to recognize something very specific, but on our deposit scale, on the regional district scale, we don't know all the different deposit types on there, so we're very restricted in what we can teach it. If you teach a machine algorithm to recognize swans and you feed it a million pictures of white swans, and the next day you show a picture of black swan, it's not going to see it. So we want it to see every kind of species of bird that's available on our property here. And the data is of uneven quality. So here we have an example. We probably have a regional mag survey with 400-meter lines, and then over a very small area, we have a ground mag survey with over 50-meter lines. So how do we can't simply feed that to the machine learning algorithm because he might see results in that small sector and focus all of his attention there. Our only positive results are where we have this mag survey, so you have no chance of identifying anything anywhere else. So there's ways of dealing with that, and those are some of the challenges we have to use. So generally speaking, exploration data is pretty tough to work with. The first conversation you'll have with a real machine learning expert is he's going to come away from the meeting with double facepalm. So what are some of the requirements we want to insist when we're setting up a program where we want to make these predictions? First of all, we need to make sure we have robust interpretations, very, very susceptible to garbage in, garbage out. Secondly, a lot of the different machine learning algorithms are very opaque. So it's black box. You put in the data, it's crunching, and then out the other end you have a result. And it's really hard to pick out, or sometimes it's impossible to pick out what features it used in the data to make that prediction to drill in one area or another. One example is the deep neural networks. It's deforming the data in so many ways that the result is really hard to understand. There's sort of a division in the machine learning, the community, and people who don't trust it because they can't understand why it's working. But it tends to work so well that they don't have a choice but to continue in pushing that forward. We need to quantify the benefits. So if it's no better than random, then we should just move on. We need to maximize the true positive value. So that's measured as recall. So we want to have the fewest holes possible to find the ore. And then on the other side of that, we also want to not miss any deposits. And usually that's a trade-off. So you have levers and knobs in any machine learning technique that you can adjust whether you're going to favor the recall or the precision. And if you don't know what you're doing, then you could only predict what you already know, which is not useful, or you predict everything else, and that's not useful either. So to demystify machine learning, many of you already know what it is, and I've had this explained to me by many experts in a way that a simple geologist as myself can understand. But essentially, if we dumb it down to two variables and examples of success and failure, so in orange here we have examples of ore, categorically drilled into ore, and the blue we have examples of waste. And the machine learning algorithm simply draws a line. It's figuring out how to separate or classify. So this is one type of machine learning, is classification, but in a lot of the cases, what we're doing is a classification problem. Most of our data is not so simple. If we had that correlation, then we wouldn't need machine learning. So we have other features or variables that are not as helpful. And then we can take that data into three-dimensional space. So now instead of a line separating good from bad, we have a surface, and that surface can have bumps and grooves and different things to capture that. And by combining a lot of different data, then we can have a more robust and a better predictor. And obviously, when we're doing machine learning, we're in plus, plus, plus dimensions. We're on 3 dimensions, we're in 10, 20, 100 dimensions. And obviously, for our simple human brains, it's really hard to work in that space. But the machines don't have a problem. So I'm not going to go through this list. If you're interested, the paper's on the USB key that you have. But essentially, you need to make sure that the data is valid. Go through the step of separating out a training set and a test set. So the test set is a subsample of your data that you've classified. You know conclusively that it's waste or ore. And then you come back after the fact and you verify whether it made the same predictions on those random test set that you set aside in the beginning. And at the very end, you need to really make sure that you vet the targets, use your geology brain to try to figure out what the machine learning is predicting, why it's predicting that, and then to make an intelligent decision on how you're going to set up your drill program. One of the problems or one of the advantages and disadvantages of different machine learning techniques is the level of fitting. So a very simple algorithm, you draw a straight line through the data and that defines positive and negative. We all can do better than that. And we can do overfitting. So we can challenge the computer to say, classify it perfectly. And what it'll do, it'll create a very complex algorithm that separates positive from negative, but it's going to overfit. So in this case where we have a real life example that's sitting here, it's not going to choose it, it misclassifies it because we try too hard to train it perfectly on our training set. And that will eventually result in a model that's much more complex. So it's a Goldilocks situation. We have some levers that we can push and pull and knobs that we can adjust and make sure we have a good balance between the precision and the recall. Most people here are interested in the application of machine learning to exploration. So what we did for the contest, we subdivided the entire property in block sizes of 50, 50, 50 meters. And then each one of those blocks has a score. Again, we used a weight of evidence, classical method, geological experts, and we tried to weight the factors that were most important. And then in parallel, we ran the machine learning, and we were able to compare those results. The machine learning algorithm that we used, and this was Doug Hatfield, who's a chemical engineer with the geometallurgical group at SGS. So he had been playing with this, and it's a very interesting and after the fact, a little bit fortuitous that this is what he had been playing with because it's very well applicable to the problem at hand. Quite robust in terms of it's not going to predict things that are impossible. It has to fit in the realm of possibility. It also uses something like principal component analysis to reduce the dimensionality. We think that the newest, greatest computers are so powerful we can throw 100 variables in there and 1,000,000 blocks and it's just going to crunch, and an hour later you come back from your coffee break and it's done. As soon as you add more and more variables, the problem becomes exponentially more difficult, and we sat beside the computer for hours and hours and days waiting, and you have to eventually give up and stop and reduce the number of variables you're allowing it to see. And so using something like principal component analysis at the beginning is really quite useful. And it also uses something along the lines of co-rigging to sort of fill in the gaps and understand, the distribution of data is not perfect, so let's do our best to try to fill in the gaps in the data before we let the machine learning advance. So I've talked mostly about classification. So you know what you want. You want ore and you want to classify the waste. You can also use machine learning to you feed it not knowing what the answer is that you're looking for. And one example of this, and I think we're going to see more of this, is using phylogenetics. So looking at other sciences that are already doing heavy big data and looking at what they're doing. So in this case here, this is my colleague Jean-Philippe, basically took, in this case was sedimentary basin. He was looking to see if he could tag which sediments in a layer cake situation were related to each other and which ones were not. And if you plot it in this way, basically the branches, the proximity of the branches indicate the strength of the relationship between the different rock units. But you could do this for alteration, so looking for packages of alteration, and it does an amazing job. Even if you don't know anything about the geology, you can do this type of exercise and it'll make you a nice lithological table the names are not real. You have to go back and check whether it's real. But a very quick way to understand what are the different classes of data you have. So what's next? We're not done hearing about machine learning. We will see it everywhere. If you watch the keynote of Apple, they've installed a chip specifically for machine learning inside the phone itself. So Siri will understand you and hopefully will make the right decisions on whether you should continue to live or not. So what's next? I think, as far as I know, and I'm not very deep into the community, but I think no one has yet sort of plunged into trying to get the nodes or the blocks to know where they are in space and what their relationships are, to see vectors towards ore. So in this case here, we have a pore-free alteration system, and you can say, well, I know that you're a phyllic alteration, but we're not at the stage yet where, well, that's interesting, go look for the next level of alteration and vector me towards where I should be paying attention. Or spatial periodicity, so we've all sat at the bar with a geologist, and he said, I know where the next deposit is because I see this pattern, thump, 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 and there's nothing here, so we got to drill under the airport. And the machine learning may not need a beer to spell that out for us. And I think that the big one is going to be teaching sort of a global machine learning algorithm which will learn the different deposit types and level the data in such a way that we can make inferences about where in a total greenfields environment. So we'll take information, that's Mauritania there, and we can say, well, a gold deposit in Archean rocks is a gold deposit in Archean rocks. Given the surface conditions, and we can re-level the mag, what would it look like in this environment? And then make a prediction where we need to drill to hit those targets. And I just threw this in last night because I love this example. So this is the worst case scenario, and this is not a real example, but if you feed into a machine learning algorithm, air photos, this is Google Maps, of different inside of your data set, you have mag and all sorts of real geological data, and you say, learn me where to drill the next hole. So in the topography, it'll see this pattern, beautiful blue lakes, lots of surface disruption. These are all examples in the Abitibi. And what will it predict? So this is a Timmins golf course, like, wow, this looks exactly like all those other things. And you might ignore all the real geological data and go straight to this, and oh, look at this one, geez, the municipal dump. So this is the type of thing where I think it's really important that we have systems in place to make sure we understand what the machine is predicting. And this is completely possible. And so that's all I have to say. Thank you.
No time for questions. If you want to talk to Guy, he can be around after. And please take a look at the publication. There's a lot more on several of these talks. There's very extended abstracts available.
And if you're looking for me, just Google my name on LinkedIn. It's one of the advantages of having a very unusual name, is you will find me. Thank you.